Hello and welcome to Enzyme Kinetics. This video is going to go into enzymes with more depth than my previous video on proteins. This is meant for biochemistry classes and MCAT prep level biology. So, to review, an enzyme is a biological catalyst. What it's going to do is, if we are tracking energy and the progress of the reaction, if we have reactants here and products here, they have to go through a transition state. This transition state is high energy, and it's always going to take energy to get to, even if your reaction is exergonic. This energy is known as the activation energy, or EA, and it's defined as the difference between the reactant energy and the energy of the transition state. What enzymes are going to do, what any catalyst will do, is it will keep the reactant and product energies the same, but it will lower the energy of the transition state, thereby lowering the activation energy and decreasing the energy we need to give our reaction the push that it requires in order to actually go. Another important thing about enzymes is that they are recyclable, meaning that you can use one over and over and over again, and it will never get used up. Enzymes are not permanently chemically altered by the reactions which they catalyze. Another important aspect of enzymes is called the induced fit model. So to quickly review this, the induced fit model says that the enzyme is not typically in a shape which accommodates the substrate. So maybe the enzyme looks like this and the substrate looks like that. Upon binding, the substrate will take the form of its transition state, which maybe does look like this. That's the induced fit. But now to get into the more fun stuff. Enzymes go through a series of equilibria in which they interact with substrate and product. So we first start with enzyme, which I'm going to denote as E, and substrate, which I'm going to denote as S, separately. These can come together in a reversible reaction to make enzyme-substrate complex. This enzyme-substrate complex can further turn into an enzyme-product complex, and this can dissociate again into enzyme and product. Every one of these reactions has a separate equilibrium constant, and sometimes textbooks will denote it as K1, K2, etc., and they might have K-1, K-2, which denote the equilibrium constants of the reverse reactions. The point of this is just to tell you that the enzyme and substrate are interacting reversibly, and to tell you that there is a complex that they can make together. When we discuss enzyme kinetics, we like to look at the Michaelis-Menten model. The Michaelis-Menten model, developed by Leonor Michaelis and Maud Menten, looks at the enzyme reaction velocity at constant enzyme concentration and varying substrate concentration. What does this mean? Well, this means that we can graph the reaction velocity, which we call V, versus the substrate concentration, which we denote with S in brackets. This makes a characteristic shape called a hyperbola. So this is a hyperbola. That means that we have an asymptote, or a graph that approaches but never reaches a certain value. In this case, we call this value Vmax. Vmax just means the maximum velocity that the reaction can reach. Why is there a maximum velocity? Well, to look at this, we have to look at something called saturation. Let's say I start with 10 enzymes as shown. If I first start adding substrate, that substrate is not going to bind to all my enzyme. There will be some substrate by itself and some substrate bound to enzyme. As I increase the concentration of substrate, more and more enzymes will be working to catalyze a reaction at once. If I increase my concentration enough, what's going to happen is something called saturation, where all the enzymes are bound to substrate. If all my enzymes are now bound to substrate, what happens if I keep adding more substrate? Nothing's going to happen. My reaction's not going to get any faster because all my enzymes are working as fast as they can. How could I fix this? I could add more enzyme. That's the only way to fix a saturated solution to go faster. If I add more enzyme, I increase my maximum velocity, or Vmax. Another important value in the Michaelis-Menten curve is called Km, or the Michaelis constant. The Michaelis constant comes from looking at Vmax, dividing whatever value that is in half, and coming to 1/2 Vmax, and looking for the substrate concentration at that value. So for example, here would be Km. We can also express this graph mathematically. We can say that reaction velocity is equal to Vmax times substrate concentration divided by Km plus substrate concentration. This is the equation that makes the curve shown. Another useful way to analyze enzyme kinetics is called the Lineweaver-Burk plot. In the Lineweaver-Burk plot, we take an inverse of the reaction velocity, or 1 over V, and we graph it against the inverse of substrate concentration, or 1 over S. Now, if we look back at our equation here, we can just do the inverse of both sides to get the Lineweaver-Burk equation. So, 1 over V equals Km plus substrate concentration over Vmax times substrate concentration. We can further split this up into 1 over V equals Km over Vmax times S plus S over Vmax times S. Notice that we can cancel out S, and we can also split up the fraction on the left. Notice that that puts us in a form of y equals mx plus b. So our y-intercept is going to be 1 over Vmax, and our y is 1 over V, and our x is going to be 1 over S. So I'm just going to erase this for our convenience. So it turns out that if we graph the Michaelis-Menten curve in a Lineweaver-Burk plot, it's going to give us a line. We already established that this y-intercept is going to be 1 over Vmax. So the higher the y-intercept, the lower the Vmax and the less effective our enzyme. The x-intercept, as it turns out, is going to represent -1 over Km. One thing I forgot to mention about Km before is that the higher Km, the less effective our enzyme. Km is actually a measure of the enzyme affinity for the substrate. So notice that if I take this curve and I graph it so that I reach Vmax sooner, the Km is lower. So in the Lineweaver-Burk plot, if we have a Km that's over here, 1 over Km is higher, the magnitude of it, I know it's negative, but 1 over Km, the magnitude is higher, so the Km is lower, so that would represent an enzyme with higher affinity for its substrate. Now, why do we care? Because the Lineweaver-Burk plot, as it turns out, is very good at helping us categorize enzyme inhibitors. An enzyme inhibitor is a substance that makes an enzyme worse at performing its function. One type of inhibitor is called competitive. Competitive inhibitors are going to bind to the active site of an enzyme, which is where the substrate binds. So competitive inhibitors often try to mimic the substrate. An enzyme affected by a competitive inhibitor is going to have a Lineweaver-Burk plot that looks like this. The -1 over Km is closer to 0, which means that the Km is higher. That indicates a worse affinity that the enzyme has for its substrate, which makes sense if it's inhibited, right? But then why would the Vmax be the same for a competitive inhibitor? Well, picture this. Let's say I have 10 enzymes and 10 substrates. Things are fine. Now I add 10 inhibitors. Things are not so good. I have as many substrates as inhibitors, and the inhibitors are probably taking up half the enzymes while the substrates take up the other half. Now, what happens if I add 100 more substrates? Things are a bit better, right? What if I add 1,000,000 more substrates? Now my inhibitor concentration is so small, it shouldn't really matter in the grand scheme of things, and my Vmax should be about the same. Let's move on to the next type of inhibitor, which is called non-competitive. So for a non-competitive inhibitor, we are going to alter the Vmax. The Vmax is actually going to be smaller because what's going to happen in a non-competitive inhibitor is it's going to bind to something called an allosteric site. Allo means other, steric means where you are in space. So an allosteric site is somewhere on the enzyme besides the active site. This means that we no longer have direct competition and we should be able to bind our inhibitor to our enzyme regardless of the substrate. This is going to cause the Vmax to go down. So my non-competitive inhibitor is going to have a 1 over Vmax that is higher. The Km, however, in a non-competitive inhibitor stays the same. Therefore, the line for a non-competitive inhibitor is going to look something like this. There's also a type of inhibitor that is called a mixed inhibitor. So here I want to address something that I didn't mention before. The competitive inhibitor binds only to the enzyme, not to the enzyme substrate complex, because the enzyme and substrate cannot be bound when the competitive inhibitor is there. The non-competitive inhibitor, as it turns out, only binds the enzyme. If the non-competitive inhibitor is bound to the enzyme, the substrate will not be allowed to bind. Therefore, there is no complex between the non-competitive inhibitor, the enzyme, and the substrate all at once. In the mixed inhibitor, you can bind the enzyme, but you can also bind the enzyme-substrate complex. That makes things very interesting. So for the mixed inhibitor, you are going to alter the Km, and you are going to lower your Vmax. The interesting thing about altering the Km is it could be higher or it could be lower, and we don't know. It entirely depends upon the enzyme and upon the inhibitor, and if the question does not tell you, you don't know. But one possibility for a line made by a mixed inhibitor could be a line that goes like this. The only stipulation for a mixed inhibitor is that it crosses the line of the regular non-inhibited enzyme at a point that is not 1 over Km and is not 1 over Vmax, so it's not one of the intercepts. One last type of inhibitor is called uncompetitive. Careful not to mix this one up with non-competitive. The uncompetitive inhibitor binds only the enzyme-substrate complex, not the enzyme by itself. This is going to cause a line that looks something like this. The characteristic of an uncompetitive inhibitor that defines it on the Lineweaver-Burke plot is that it is parallel to the uninhibited enzyme line. They never cross. So for an uncompetitive inhibitor, you will see two parallel lines, and that's how you know. There's one more interesting thing about enzymes and kinetics that I want to address. And for this, I have to go back to a Michaelis-Menten plot. So to refresh you, this has V on the y-axis and concentration of substrate on the x-axis. And the concept that I want to address is called cooperativity. In cooperativity, you deal with an enzyme that has multiple subunits. So let's say that my enzyme looks like this. And I have 4 subunits, and they all have a certain shape to their active site. In cooperativity, the binding of one substrate is going to help the binding of other substrates. So let's say that that binds, and it changes the conformation or shape of my enzyme to look different. So I'm going to try to draw triangles now for my active sites instead of circles, if that's not clear. And all these enzymes, the subunits, they're supposed to be associating. So if I didn't make them touch, they're supposed to be touching and associating with each other because that's how they affect each other's conformation. So now I have a substrate bound, and all the other active sites are more conducive to the binding of other substrates. This creates a shape called sigmoidal or logistic. The reason that it's called sigmoidal is because it looks like an S, and the reason that it also may be called logistic is because it's logarithmic in its function. But if you see this type of S-curve, you know that your enzyme is cooperative. Cooperativity may be affected by certain factors, and I want to make a video in particular on the protein hemoglobin, which binds oxygen in our blood, and that's affected by several different factors. And if your cooperativity, or if your cooperative enzyme gets worse, what's going to happen to your curve is it's going to shift to the right. That means you need more substrate concentration to reach the same velocity. So I hope this helped you understand enzymes a little bit better. Thanks for watching!